Okay, in the last class, we started off with interfacing circuits. We saw schematic triggers and a few other interfacing circuits. Today, we are going to learn about level shifters and I/O pads. Okay, there is many of the PCBs. Even today, they use a lot of TTL gates. So there might be a requirement to interface the TTL signals with CMOS circuits, right? So the signals coming from TTL logic family, if you see here, the VOL and VOH for a TTL is an 0.8 and 2. So you don't get a rail-to-rail output in TTL, which we discussed even in our first class. So the output for low condition could be anything between 0 to 0.8. And the output high could be anywhere between 2 to 5 volt. Okay, so it is not symmetrically placed across VTC, and there is a band of voltages for VOL and VOH. And for VOL it is 0 to for low voltages, the range is 0 to 0.8 for output equal to low, and from 2 to 5 is the high voltage range output. Okay, so that needs to be now interfaced with a CMOS circuit. So in CMOS circuit, if you see here, we need to adjust the threshold voltage for a proper interface. We need to adjust the threshold voltage of the CMOS inverter so that it is exactly in between 0.8 and 2 volt. Okay, then a proper interface can happen. You can't have if CMOS circuit which is operating, again this is operating at 5 volt. I am interfacing it with a CMOS circuit which is operating at 5 volt. I cannot keep the threshold voltage as 2.5 volt, right? Then you will find that and this won't work properly, right? If I keep a threshold voltage of 2.5 volt, if the output from the TTL is 2 volt, it is 2 volt, and it may not take it as 1 at all, because you are set at such high threshold voltage. So now for this circuit, for when you are integrating TTL with CMOS, it is best to have an inverter, CMOS inverter threshold exactly in between 0.8 and 2 volt. Okay, so that is what is an inverter threshold. That from our VLSI classes we have learned that this is a CMOS VTC curve, right? So if you draw a line in which V in is equal to V out, that is at 45 degree from this x axis, it will intercept this x. So this is known as the inverter threshold voltage. Okay, we are roughly, if you want to say that any voltages which is below Vm, okay, will be taken as 0, and anything above Vm will be taken as 1. So if you just approximate this curve, this as a vertical line, then you can call it that way, right? Now how to compute an Vm? So again, this derivation also is there in our VLSI class. So what we do is we equate the currents in this NMOS and PMOS. So the current in NMOS is given by K divided by 2 VGS minus VT the whole square plus 1 plus lambda. So this is channel length modulation. So if I neglect this channel length modulation, so the current becomes an ID is equal to, through the NMOS it becomes Kn by 2 VGSN minus VTN square is equal to again Kp by 2, because these mobilities of the PMOS and NMOS are not the same. So I write Kp by 2 VSG. Now this is the voltage out here, VSG, and then VTP, the threshold voltage out here square. Now if you see here VGS, now we are interested in computing the threshold switching voltage, right? At that particular condition, we are assuming that current is flowing, the current which is coming from PMOS is going through the NMOS exactly in the middle of the VTC curve. Okay, for that condition, we take VGSN is equal to, we are assuming both the transistors will be in saturation at that particular point, right? So V in is equal to Vm, we take that particular condition. So we are going to substitute VGSN with Vm, whereas for the PMOS it is Vm out here and it is VDD out here. So the gate source to gate voltage will be VDD minus Vm. So this VDD minus Vm. So if I substitute that in this particular equation, so I get an Vm is equal to VTN plus R VDD minus. So this is the equation for Vm, right? Generally for an CMOS inverter, what do we do? To get a symmetrical threshold voltage, we target Vm to be VDD by 2, and that we obtain by keeping VTP and VTN same, and we keep R equal to 1, right? And R from this equation, if you see here, now R is nothing but Kp, root of Kp by Kn, right? So now in this particular example, we are not interested in keeping a Vm as VDD by 2, but we are interested in keeping a Vm at 1.4 volt. And where did this 1.4 volt come from? Because from the TTL, right, requirement. This is 0.8 and 2 volt here. So we want to keep a threshold voltage in between. So that is the reason I have taken 0.8 plus 2 by 2, average 1.4 volt. So this becomes a Vm now. VDD is 5 volt. And for a particular technology, if it says VTN and TP is 1 volt, magnitude are 1 volt, then I can put these values as 1, 1 and compute the value of R to be 6.5, right? So this is the R value. Now we also know that R is root Kn by Kp. So you can Kn is nothing but mu n Cox W. So this we learnt in our VLSI classes, right? If you have doubts, you could refer to my VLSI lectures. Okay. So if you see here, now Cox is generally the same for all the technology, for the PMOS and NMOS, so they get cancelled, right? And the mobility of the electrons is generally 3 times the mobility of a P. So I put that P, and then R is you remove the square root by putting an R square, so you get, so you will find Wn by Wp. If the lengths are same, it has to be 169 by 12. That means the NMOS width has to be, if the lengths are same, then the NMOS width has to be 169. NMOS is to the ratio of NMOS and PMOS has to be 169 by 12, right? That means the NMOS has to be very much larger compared to the PMOS. Okay, that is understood, right? If you see this VTC curve here, if you keep the PMOS width generally twice that of NMOS, you get a symmetrical VDD and you get a VTT as 2.5. But what is this VM? This VM is close to 0, right? It is 1.4 volt, right? So that means this curve we have shifted towards the left, and if we have to shift it towards the left, we have to make NMOS much stronger, right? So that is where this is coming from, right? So this particular thing is applicable, okay, for only when VTN is 1 and 1 here. Okay, if it is now say 0.9 and 0.9 or 0.7 and 0.7, then these values will accordingly they will get, the value of R will change, and accordingly this ratio will change. So you have to accordingly find out what will be the ratios. Okay, so now this is another level shifter. Now here we are talking, in this particular case, the sign of the signal changes, like it gets inverted. So because we are using an inverter here, so if you don't want that to happen, then you can use this kind of circuit also. So you have an input out here, and then that is this is the inverter. Okay, and now but this inverter is cross coupled with one more inverter out here. So it is, so whenever the input signal is going high, this output voltage will become 0 here, right? If it becomes 0 here, this PMOS will be turned on, and this will be that will in turn turn off this. So this will get faster switching is possible, and again you are using one more inverter, so that this signal gets again here you have an A bar here, you will as X, you will get back A here, right? So in all these circuits, like we studied earlier in schematic also, these cross coupled ensures a positive feedback. So it will it becomes a metastable circuit. That means it is stable either in 0 or 1. They act like a flip flop or a latch. Okay, so a small input change will trigger the change from 0 to 1 in a positive feedback network. So the switching will be fast. So that is why we use this cross coupled topologies. Right. Now if you see here, there will be certain requirements where within CMOS also different VDDs will be used. So suppose we are moving, we have some circuit which is operating at with 180 nanometer technology, so the VDD will be 1.8. We can have some part of the circuit and it might have a lower technology, some on the PCB, some chips which are operating at say 1.2 volt and which is 90 nanometer or 45 nanometer. So there will be a requirement to boost up these signals to that. To bringing down the voltage levels is easy, right? But from 1.2 logic level to get it to 1.8 volt logic, then there is certain issues which we will discuss. So that is why up conversion we are discussing. Down conversion is not a very major issue, right? So now if you see here, there could be not only for different technology, within the same technology node also, we have learnt about dynamic voltage and scaling in our very first class, wherein some circuits which are not in the critical path, okay, so you can reduce the power supply there, so that the power consumption is reduced. We learned that the total power consumed by a circuit is a strong function of VDD. So in all those non-critical paths, you can scale down the voltage. So once it is scaled down, the output voltages also will be less, and finally when we have to merge those signals, we will have to again bring back the signals to the required level. So these are all so you have level for all those applications. We have a circuit which is known as level shifter. Okay, so can we use just a simple inverter to shift the level? So let's see what are the problems. So if I discuss the first circuit out here, it is 1.8 volt and 1.2 volt out here. So if I give 1.2 volt out here, this NMOS will be switched on and this will be switched off out here. So I will get 0 volt here, and when suppose I am giving 0 here, okay, this will be switched off and this will be switched on, because if you see here, it is 1.8 volt and 1.2 volt. So threshold voltage is 0.75. So this is this will be switched like for a 0 volt it will be switched on. When it is 1.2 volt, sorry, this will be switched off, because 1.2 volt here, 1.8 volt, so this will be 0.6 volt, whereas the threshold voltage is 0.75, so this will be switched off. So there is no issue. So this simple circuit will not take this voltage from 1.2 to 1.8 volt, right? So for 1.2, let me repeat this. If it is a 0, this will be switched off. This will be switched on, because 0 and 1.8, this will be switched on, no problem. When it is 1.2 volt, okay, this will be switched on because the threshold voltage is 0.75, and this will be switched off because 1.2 and 1.8. So 0.6 volt only is available here, whereas the threshold is 0.2 volt. Okay. Now let's take one more case. Like suppose this is an 45 nanometer technology node, where the voltage is only say 0.9 volt. Okay, in this case, when it is 0, this will be switched on. Okay, and PMOS also, when it is 0, this will be switched off and this will be switched on. And when it is going to 1 out here, right, if this voltage is, so it is only 0.9 volt out here, and you will have 1.8 volt here. So now this voltage, okay, across the gate source will be 0.9 volt. That means this also will be switched on. So when VDL is high, both this will be switched on, and you will have a current which is flowing from VDD to ground, and you don't get the desired output out here. So for this particular configuration, so this cannot work. That means whenever the difference between the VDD high and VDD low is greater than the threshold voltage of the PMOS, a simple inverter level shifter won't work. Okay, so let me repeat it. Suppose it is 0.9 volt out here, then this is 1.8 volt here. So now you will find this NMOS is switched on, because this is I am giving 1 here, I want a 0 here. So this is switched on here, right? But what about this PMOS? Normally it should be switched off, but it doesn't get switched off because you will have a 0.9 volt out here now here, and this is just threshold voltage is 0.75. So this also gets switched on. So this circuit won't work. Okay, so that is one issue. Further, if I go lower voltage, okay, 0.7 volt. Suppose I take in this case, another issue also creeps up. That is the threshold voltage required for this is 0.75. So there is no adequate threshold voltage also available to switch on this transistor properly. So you see that for when we can't use a simple CMOS level shifter to shift the voltage, it is possible in certain conditions. Okay, so if these two voltages VDH and VDL are close to each other, then it is possible. But the moment there is a huge gap between VDL and VDH, then a simple inverter won't work, and we need to use a slightly better circuit, which we are going to discuss now. Okay, so this is one kind of level shifter which was proposed by these people out here. So here, if you see here, what is being used is, this is the low input which is coming out here. I am using an inverter out here, right? And then I have an so both these circuits, this voltage and this voltage is corresponding to the low levels out here, which is given to the NMOS, and here you have an higher voltage. So VDDL corresponds to the low VDD circuit, and VDDH corresponds to the higher VDD circuit. And here and then you have an cross coupled PMOS out here. So if you see here, what happens is this acts like an latch. So since if you give a small input voltage, okay, which is above the threshold voltage, then this transistor starts conducting here, and the fall in voltage out here will reduce the current in this branch, and that will subsequently increase the current. No, so if this voltage is increasing, this voltage will fall down, right? So this will be switched on. Okay, once this is switched on, so the current will flow here, and since it is cross coupled like this here, this voltage will start increasing. So this will be switched off now. So you will find that here these are cross coupled. So that is why it acts like an positive feedback network, and quickly it will get into here you will get the entire VDDH. So you can use one more inverter to get a V out, because this is an inverted output available here out here, or you can directly take an output from here. So you see in this particular circuit, now that condition of PMOS being switched on, okay, this condition is avoided here by using a cross coupled PMOS out here. So so you can use a VDDL and VDDH. So this can be there can be a large difference between VDDL and VDDH. Okay, so that this circuit will take care of that difference. So you don't have to keep the difference below the VTP of the PMOS. Okay, here if you see here, the difference between VDDH and VDDL, if you are using an inverter, the difference should be below the threshold voltage of the PMOS. Okay, and otherwise the PMOS will remain on. So that restriction is not there in this particular circuit. Okay, but there is one issue will be there, that this has to be this will work very slow in case the V in is much lesser than if it is lesser than the threshold voltages of the NMOS, because this voltage is supposed to, whether it is here or here, this is at both these nodes, it is the low voltages which are available, and hence they need to switch on these NMOS transistors, right? And hence so it has to be more than the threshold voltage for it to function. Okay, even if it is less than threshold voltage, because of some sub-threshold currents, it will do a switching, but it will be very slow out here. So that is one restriction with this circuit. So is this circuit understood by all of you? Yeah, yeah. Is it okay, Nagaraj? Yeah, Prerna, Anurag, is this understood? Yeah, okay. See what we have here. This is a high. Say suppose this is 1.8 volt. Okay, and this is, say, these two voltages is just the this voltage is just 1.2 volt. Okay, so now this logic which is what we are getting is from 0 to 1.2, we need to convert it to logic level 0 and 1.8. So we are using this particular network. So suppose this is 1.2 volt which is applied here. So this NMOS will get switched on. So this there will be low voltage. This voltage will start dropping. Okay, because you have applied, you have switched on this. So so you will find this gets an switched this low voltage. Now this voltage will start since it is low. This MP 2 will start switching on, right? So the low voltage here will switch MP2 on. So if this is getting on, right? So this voltage will start increasing, and that will switch off MP1. So this is just a cross coupled inverter, right? So if this is getting switched on, this will get switched off. So this switching off will again pull up this Q1 node to high. Okay, so now you will see, and this is switched off because you are giving 1 here, so this is switched off here. So this is a crossed couple. This works like just like an latch. Okay, so only thing is the input levels out here is low. Okay, so that is the only difference. So this is an latch only, if you see here. Okay, only thing is the input levels what we are applying out here is lower than VDDH. Okay, so this doesn't have the restriction of the difference between V in and VDDH to be less than VTP. Okay, so that restriction is not there in this circuit. Okay, it can still work. Okay, however, MP1 will pull Q1 high, right? Because that will get an like if this becomes an if this gets an switched on, right? This becomes an 0 out here, right? Okay. So this becomes an 0, and this comes as this is going to be switched on. Yeah, okay. This is switched on, and then this is 0, this is switched on, so this will be so this gets switched off, right? Okay. It's an cross couple inverter only. So you have an 1 out here. Yeah, if it is 1 out here, it will be 0 out here. This will be yeah, this will get switched off, right? If it is 1 out here, it will be 0 out here, right? If it is 0 out here, and this will be switched off. If it is 0 out here, this node will get charged to 1. So you have 1 here. So MP1 gets switched off, right? So this will this Q1 will go to low whenever it is 1, and then you have an inverter, so this goes high. Is it okay? Right? Similarly, if this is low out here, this will be switched off, this will be switched on, and since this is switched on, this will become 0 out here. So that will switch on this MP1. So this Q1 will get will get charged to VDD, and then you get it 0 out here. Is it okay now? Okay. So okay. So now if you see what we said, the advantage of this circuit with respect to an inverter is that this voltage VDD and this can be far apart also. It can be greater than the threshold voltage. The difference can be greater than the threshold voltage of the PMOS. Okay, so that is so this is one circuit available here. Now this is a modified circuit which was again published in this paper, in which what they have done is so this can work below the threshold voltages also. This circuit, we said VDDL has to be above the threshold voltage of these two transistors. Okay, so that is the one of the restrictions with these circuits. So now this particular circuit can work at slightly below threshold voltages also. Now if you see here, this actually they have claimed it works till 0.18 volt also. Now if you see, this is an input, it's an inverter out here. This is also an inverter. You are giving and you are using VDDL to generate V in plus and V in minus. Okay, so these two voltages are given here, right? Now this particular inverter, we can't, obviously, since it is below threshold voltages, you can't give VDDH out here, VDDH out here, right? Because then the voltage across this PMOS will be, even when V in is high, this will not get switched on. So there is a requirement to get a lower voltage at these two nodes. Okay, and we also saw that in our schematic trigger design, when we discussed that inverters can work at sub-threshold region also, right? And provided the VDD also has to be brought down accordingly. Now here if you see here, so to bring down the VDD, what has been done is an diode connected and PMOS have been used out here. Okay, what is the diode connected PMOS? If you see here, this is the way, and it is an HVTs have been used. Okay, so they had not mentioned these figures, but for a 90 nanometer technology, since they mentioned 90 nanometer technology, I picked up these specs from the 90 nanometer. So if I put that, if you find here, this is an diode connected HVT. So when you use these PMOSFETs as diodes, you will find this much voltage being dropped across these PMOS. So you will find the voltages available here now will be around close to 0.45 volt only here, right? So now this becomes 0.45 volt becomes the VDD which is available for these two small inverters, which we are going to operate at 0.8 volt, right? So now here if you see, the voltage is only now around close to 0.45. This voltage is also 0.45 and this is around 0.2. So this voltage across here, now it is not 1 out here, it is just 0.45. So that will ensure that these inverters work proper. Okay, if you apply 1 here, then for 0.18 this step P transistor will not be switched on. So we are dropping this voltage out across these two inverters by using an PMOS in a diode connected pattern fashion. Is this the aspect clear? Then these two works like an inverter. Okay, now once you have an inverter, you give an cross coupling so that the switching is faster. So whenever we give this kind of cross coupling, the aim is to give a positive feedback, and that makes, whether it is this circuit or it is this circuit, whenever we give a cross coupling, it makes this as an latch, okay, or a metastable circuit, which can be either stable at 0 or 1. So it will quickly change from one state to other because there is a positive feedback which has been introduced. So the purpose of these two diodes, diode connected PMOS, is just to scale down the VDD here, right? So now if you see here, this particular output, okay, so for logic 1 it will be around 0.4. Now from 0.8, now this logic level has come to around 0.45. Okay, and that we are using like a normal inverter out here to again get back to the 1 volt system, right? So it is like one set of inverters where I have an V in of 0.18, then I get around 0.45 here, and then I get the full voltage V here. Now here they have used, in this particular work, they have used two PMOS in series to reduce the current. Okay, they have used minimum width of the transistors, and also to increase the length, they have used two transistors like this in this particular circuit. So this is just I have redrawn this circuit based on this paper. So this is how they have done. Okay, so but this advantage of this particular circuit is it can work at below threshold voltages also. Is it clear to all of you? Yeah, shall we move forward from here? Okay, so you have two inverters which is working at sub-threshold region. These input voltages are of the range of only around 200 millivolt, 1.8 to 200 millivolts. But to get down these supply voltages, if I apply 1 volt here, 1 volt here, and it is 0.2 volt here, 0.8 will be the voltages available here, right? So this PMOS will be switched on. And another thing which we need to see out here is these are low voltage and low threshold voltage devices, these 1, 2, 3, 4 and this, because this part of the circuit, and this inverter, they are working in sub-threshold region at low voltages, right? So that is the reason we are using low voltage devices in these circuits, right? And here we are using high voltage devices so as to ensure that maximum drop from 1 volt. We are using, we want to bring down the VDD, so that is why we are using HVT devices out here, and this is a normal VT devices. So here we are targeting from a shift of 0.4 to 1 volt only. So that is why this configuration has been used. Okay. No, when we are using low voltages, if you use high voltage devices out here, then the switching will be very slow, right? So to ensure that this particular circuit inverter works fine, right? Because the VDD here is only 0.4 volt and the input voltage is only 200, right? So to ensure that these circuits have adequate current and faster switching, we are using LVT devices out here in these circuits, because the voltage levels are low. Yeah, because the operation of these transistors are at low voltages, and that is the reason we are using low voltages for switching. Okay. Now when we have an now we are talking about some input output and interface devices. So we have something known as electrostatic discharge. Right? What is that? Suppose you have an chip, okay, and human body, when we walk, we can accumulate as much as 1.5 kV of static voltage can get accumulated in our body, and then with bare hand, if you are trying to touch the chip, those chips can be subjected to that high static currents, and it can destroy the circuit. Okay. So some interface circuit needs to be put between the chip and between your actual silicon chip and your the physical chip. Okay, so there will be IO pads. Okay, between your actual circuit and the pins of the chip, there will be some IO devices which will prevent such high discharge into the CMOS silicon chip, and to prevent it from getting burnt out. Okay, so this is the model of human body. Okay, for simulation purpose. So once we design a chip, we will test it whether and what happens, and we will incorporate a protection circuit which will take care of which will withstand the human body touch also. So right, even if somebody touches the chip with bare hand, it should not get burnt out. So in between you will have an interface unit. So these are some of the models which are used. So you have an VESD. So initially you charge this capacitance to the full voltage, and then you put the switch out, shift the switch here. Okay, then you will have to see whether this circuit there is no burnout in this circuit. Okay, so these kind of simulations are done. Okay, before we and then the IO circuit is accordingly designed. So this is under test, but from here to in between there will be an IO pad. So that IO pad has to take care that the chip doesn't get disturbed for these kind of input simulation also. Similarly, this is a machine model where the machines can accumulate a larger capacitance than our those instruments and all whatever we have on our in our lab. So they can accumulate charge up to greater charge than the human body. So this is the model which is equivalent to a machine. Similarly, like within the chip also, okay, because of the bonding wires and things like that, they could be charge which gets accumulated. So the IO device have to within the chip means within the package, okay, within the package also. So this is another model. So all these models are there for simulation purpose, okay. So we use these models to simulate and then check whether the device is able to withstand these kind of ESD signals. So this is another model which is used for testing. Like you charge this capacitance to few kilovolts, around 15 kilovolts, and then you switch it on. So you have LS, RS, CS, and capacitance. So these are all simulation parameters. So this table is given here for human body and for a machine. Okay. So when you do this, still your circuit should be able to sustain in the simulation. Only then you will accordingly the parameters of the ESD part. So in between this DUT and in between there will be an ESD. So that ESD has to protect these currents being these high currents flowing into the circuit. So even when we do these kind of switching, okay. So this is what the model for ESD switching looks like. So if you see here, this is one of the simplest way of making an ESD circuit. Okay, so what is done out here is you have an input signal out here, right? This is an diffused resistor within the chip, right? And you have two diodes which are connected here. Now, if you see here, when the input is going high, okay, this diode will get forward biased, and this voltage will get clipped to VDD. So the maximum voltage which can come out here will be VDD plus 0.7, right? So you have a diffuse resistor. So this will also prevent some maximum current which is being flown out here. So there are two diodes. One is taken from here and one is taken from here. So the reaction time will be this will operate at first, and if it fails to operate, then so there is kind of double protection. That's all. Okay, so this is the kind of two diodes which will ensure that whatever is the input voltage, the maximum voltage which will go into the die, okay, of the circuit is VDD plus 0.7 volt. Similarly, if it makes a negative spike, then this diode will get forward bias. So maximum voltage which it can go here will be minus 0.7, because you have a diode out here, right? So this diode, even if it gets for a negative spike, if it gets a forward bias, this will get forward bias. So the maximum voltage it can go is around 0.7 volt. So this particular circuit, in between the input and your actual circuit die, right, will ensure that the voltage ranges available out here will be from 0.7 volt to VDD plus 0.7 volt. Is this operation of this circuit understood by all of you? Is it okay? Okay. So this is one more circuit. Are these removable circuits? No. Actually, when you see here, when you make a design of a circuit, right, these are IO pads which are generally given by the these are IO pads. Okay, these are given by the manufacturer itself, right? So this is IO pads will have this, and there will be other. This is a small portion of the IO pad. So those IO pads will be given by the manufacturer, the layout as well as the schematic. So once you once you design your circuit, so before sending it out for fabrication, in the layout as well as in the schematic, you will place IO pads all around, where all the input signals will be passed through the. So there is an equivalent and a schematic as well as layout which will be provided by the fab lab, right? So we generally don't design IO pads; it is done by the fab lab, and like you pick up NMOS and PMOS, the same way you pick up IO pads also. Okay, so this is one part of the IO pad. There are other circuit also involved. There will be an analog IO pad, digital IO pad, but this is common. So this will be the first part of the IO, right? Yeah, it is just for additional safety, there are two, this will clamp the voltage, because the chances of this voltage going very high, the input voltage going high is very, it has got a higher probability because of switching and ESDs, right? So, so that is the reason two diodes have been placed like that. Okay. Here if you see here, this is one more circuit. So these are all actually circuits at different point of time by different fab labs, and they have tried and tested these circuits. So these are the circuits which have been that has been reflected in your textbook gang. Okay, so these are actual IO circuits, ESD circuits, by different fab labs. Okay, so here what has been done here it is like this is an diode connected NMOS. So this is clamp the upward voltage out here, okay, to VDD plus 0.7. Also there are some thick oxide transistors. These voltages are around 20 to 30 volt. Okay, so if the input voltages go about 20 to 30 volts, okay, these will get forward biased. Okay, so this is so in case there is a very large spike, so this will also come into play, and this will also clamp the voltage, and then this obviously this will work. So the entire work is not done entirely by this. So these two transistors help in, if it is going beyond 100, 200, so beyond 20, 30, in fact they will also operate, and then this will also operate. So ultimately here you will get only VDD plus 0.7 volt, but the load is being shared by these transistors also. They will clamp the output to 20 to 30 volts. So you will, because these are again connected as an diode, right? So this is connected as an diode. This is not connected as a diode, right? This will get switched on, right? So what happens if this gets switched on? You will have one large current flowing here. So you will have an IR drop across these two resistors. Hence this voltage will again come down, right? Whenever the voltage is going beyond 20 to 30 volt, M2 will get switched on. So you will have current flowing, a large current flowing in this path from R1 through these resistors. So the voltage at this point will get dropped. So these are some of the kind of circuits which we use to prevent our circuit from getting damaged because of ESD signals. Okay, so this is another kind of signal circuit which we are using. This is one, and again picture taken up from the textbook, in which it shows that because of ESD, if you see here, the polysilicon gate it has got melted. Okay, so it is so this is the melting of the polysilicon because of high voltage. And also the metal, okay, you will have metal contacts in the source and the drain, right? So that metal, because of high voltages, has got melted, and it has come into the channel region, and there is a short circuit now. So this is all permanent damage which has been done to the device because of high voltages being applied. So that is the reason these kind of circuits are employed, so that these kind of damages can be prevented. Okay, so this is one ESD circuit. Okay, the IO pads, over and above the ESD pads, it will have certain input circuits and output circuits. So there will be IO pads will generally have ESD, which will be common, and then some of the IO pads will be analog input pads, or it could be digital input pads, analog output pad, or digital output pads. So we need to use the appropriate IO pad for each of the signal which is coming into the chip. Now this is one simple circuit in which the input which is coming here is coupled to the chip here. So this is one portion of the IO pad circuit, you can say. So you have this enable bar signal here. It is enable bar signal here. So whenever this enable bar signal goes low out here, so you have an high here. So this NMOS will be switched on, and this PMOS will be switched off. So this is essentially it's just a pass transistor, right? So this signal will be now coupled to the chip. So you see here that constantly the output pin is not connected to your circuit, only when on a requirement basis, whenever there is a requirement, so that will protect your circuit, right? So only during that small window of operation, whenever you need to take an input, only during that period, this transmission gate is enabled and the input signal is coupled out here. Okay, or you could also use a simple inverter. Here you will see this analog, the input which is coming here gets coupled through this transistor. Here it is a much better isolation. If you see here, this input is just fed to a gate of an inverter. So this inverter becomes part of the IO device, IO block. So you will find that output is available, or it gets inverted here, or you could use one more inverter to get back the same polarity signal. So here the advantage out here is, suppose inside the chip the signal needs to drive a large load, n number of gates, then there will be a large current which will flow in this wire, and in the you will see that later on that there will be some bonding wires on chip, and there will be a lot of stray capacitances and parasitic inductance and resistance outside the chip also. So there will be a voltage drop in all those parasitic elements, right? So if you draw a large current through this wire, to prevent that, you can just use that input as an input to an inverter, and subsequently you can use one inverter or a chain of inverter to drive the internal circuit. And this also, because this is just driving the gate of the circuit, and this power supply is within the chip, this VDD is, right? This VDD is a regulated supply available within the chip. So the circuit is much better protected. So these are the two kind of input circuits which are used in an IO block. Then on the output side also, if you see here, you will have an inverter, finally one inverter which can drive large loads. This is the data which is coming from your actual circuit. So if you see here, when the data is and again this is not directly connected to the pin all the time. So only when we want to connect, so this signal will be given high here, right? So when this becomes 1 here, so this data gets inverted out here. Similarly, this data through an NOR gate, it gets inverted out here, and then you have one inverter here. So you will find by using a control signal out here, we are coupling this output out here. Otherwise, it will be in high impedance state. Okay, this circuit will be, because both will be right. Both will be this will be high, and if this is if suppose this is low, what happens here? You have an one out here, so it will be 0. So both will be off normally. So only when the this signal, enable signal, is high, then the data will be coupled to the output. Okay, otherwise both will be in high impedance state. So this kind of circuits can be used. The same thing can be realized only with 4 transistors also out here. So if you see here, if the clock is 0, this will be off, and this will also be off. You are giving clock bar here. So this will be in a high impedance state. And when the clock is high, both these transistors. Now, although here there are 12 transistors, there are only 4 transistors here. Because all these are all in series, they have to be sized very high. So that it can drive, because this is going outside the chip, so this should have adequate current carrying capacity for reduced delays. So the size of these transistors will be very large. Here there you will find only 2 large transistors are used. So although 12 transistors are used, this is more compact. Okay, here although 4 transistors are used, but all the 4 are one above the other, and all of them drive the external load. So all these transistors will be large. So so this is the one which is most widely used. So these kind of circuits are used in the output circuit. Okay. Now if you see here, when where a high current flows into the from to the output, okay, there will be a lot of voltage drop between the chip and the in the bonding wire. So let me show you one picture of the bonding wire. I think that will be here, right? This is your chip and this is your pin. So in between there will be a bonding wire. Okay, so this is known as the bonding wires, and these are the pins. Okay, so if I come back here, Now if you see here, the current goes like whenever we are doing an switching, you will find the current goes to an peak, and then it comes back, right, whenever there is an switching, whenever an output. This we saw in the introductory class. Whenever the output is being switched from low to high, so it will go to high and it will come back to low. So if I write the charge equation, it will be Q into C V, right. So if I talk about this position, when the current has reached the maximum, approximately the output capacitor, okay, by this time the capacitor will be fully charged to the output capacitor will be fully charged to VDD. At this point, I can assume that the capacitor will be charged to VDD by 2. So I write C load into VDD by 2, and what is this charge? This is current into the time, right? So the current is I max by 2. So the average current will be I max by 2, and this time is TS by 2. So I get I max TS, and so from this equation, I max TS by 2 is equal to C load VDD. So this is one equation which I get, right? And what is the rate of change of current here? This is the rate of change of current, right? So I max di by dt is from here to here the current is changing I max at a time TS by 2. So 2 I max by TS. Okay, so this is the maximum rate of change of current, right? Now if I substitute I max from these values out here, C load VDS TS. So I get this equation out here, right? Now if I put some values like C load 100 picofarad and TS 5 nanosecond, then I get di by dt max as around 80, okay, milliampere per nanosecond. And if the bonding wire inductance is 2 nanometer, so I will get L di by dt. So this L di by dt is the voltage which gets dropped in the bonding wire. So it is around, it comes out around 160 millivolt. So you will find that whenever there is an input switching happening, so this kind of this is an typical values have been taken here. So this is the kind of voltage which gets dropped between the chip and the pin, okay, here in the bonding wire. Okay, this is equivalent to an inductor actually, these bonding wires, okay, which takes the input from the chip to the pins. Okay, it is an equivalent to an inductor, and the voltage around the across the inverter is given by L di by dt. So we have found out a di by dt. What is di by dt? This is the maximum from 0 to I max by the time TS by 2. Okay, so this is what, and then I max and we have computed here, right, based on the node capacitance. So we substituted that. So we put some values. So we got this value. So you will find that. So it is now if you so this reduces the noise margin. Right, now if you see here in this particular equation, TS square is there. So if I want a faster switching, TS needs, suppose for TS needs to be reduced. So if I reduce the switching by half, right? So since it is in the denominator and a square, this goes up by 4 times. So you see there is a trade-off between how fast you require the switching and how much a voltage drop gets how much of voltage gets dropped across the bonding wires, thereby reducing the noise figure. Okay, so is this thing clear, this trade-off aspect? So if you do if you ensure that if your transistors are large size and you are able to push more current for switching, so high currents will result in greater drop in the bonding wires. Okay, so the output noise margins will get adversely affected. So that is the trade-off which you have to think of. Okay, so this is then output circuit issue. So you have to overcome those kind of things. You have a circuit something like this. Okay, what it does is, before this, we are going to enable this clock signal for this these two circuits to operate, right? This PMOS and NMOS to operate. But before applying CK, whenever we want to transmit a signal, we will switch on ST. Okay, ST is a strobe signal. Okay, what it does is, if you see here, it is VDD will be available here, and 0 will be available here normally. When the clock is 0 here, right? It is 0 here, it will be VDD available here, it is 0 here, again 0 will be available here because there will be 1 here. So it will be a 0 and VDD is available here. And when you give an strobe signal, both these transistors, we give a small strobe signal, okay, small duration strobe signal. So both these transistors, they both are NMOS, okay, this is not a PMOS, this is an NMOS. So both will get switched on simultaneously, and it will, this is connected here. So there is a dot out here. So this output node will get charged to VDD by 2, okay. So and then this strobe signal goes, and then you give the clock signal, okay. Then now this VDD by 2 will be either be pulled to VDD or to VDD by 2 0, okay. So you will find that there is not very high current requirements are there, because if you have a microprocessor with 32 bits or something, you will find all of the data is going high and low at a given time itself, right? So you will find large current is being drawn from the VDD line and the ground line, okay. So that this particular thing clearly brings down the entire power requirement by 50% at least, okay. Because this node is straight away first of all being pre-charged to VDD by 2, okay. Yeah, is this understood? Yeah, Pradeep, is it understood? Aman, what it does is just before driving the circuit, okay. So this is an what does this circuit do? Like let me go back here. What does this circuit do? When the clock is 0 here, I have a 0 here, right? And when it is 0 here, so it is an so it will be 1 out here. So this will be switched off. Similarly, if it is 0 out here, it will be 1 here. This will also be switched out. This will be in a high impedance state, the output pin, right? Whenever this is going high, so that will isolate the output of your whatever circuit you have designed from the pin. Only when I have to drive that, I will give an enable signal here, right? If I give an enable signal here, I will have a 1 coming here and the data coming here. So this will invert it, okay. So if I invert it, I get a D bar out here, and similarly this is 1 here, it is 0 here. For a NOR gate, if I go to 0 here and a signal here again, so this is like an inverter, and both these inputs are actually going to be a D bar. So I get back a D out here, right? So this is just an and this isolates the D and from this point whenever the clock is 0, okay. Whenever the clock is 1, so this inverter starts functioning. Now the problem is, now if you have an n, like for the 32-bit data line, okay, so all of them are going to at the same time and are going to get charged to 0 or 1. So there will be lot of current which will be passing through the VDD IO pads and through the VDD rail and through the ground rail, okay. So to prevent that, what we just before driving the output, so all these output data lines will be pre-charged to VDD by 2. So how it is done? So before the clock signal goes high, you give a small strobe signal. What does a strobe signal do? If when the clock is 0, you will find this is 1 and this is 0. So if you see here, and both these transistors are off, okay. This is also off because the clock is 0 here. But when you give the strobe signal high, between VDD and ground, you will find this is a small pulse which is given here. So you have two NMOS which are connected in series with their symmetrical size. So when you give the strobe signal, this output voltage out here will at this node it will become VDD by 2, okay. And then this strobe signal goes, and then the clock is going high. So depending on the data, now this signal has to go from VDD by 2 to VDD or from VDD to 0. If data is 0, this will discharge. So you will find here the total switching requirement is not full rail to rail, but the switching requirement is only half rail to rail. So that helps in reducing the power consumption. Is it okay, Anurag? No? Okay. So these kind of circuits are also used. Now, static power, it doesn't, just a small strobe signal is given to charge this to VDD by 2, okay, that's all. just before the clock is enabled. Okay, so we are staggering that. That's all. The switching is been staggered into two phases. Okay, the two NMOS will act like the two NMOS will act like resistors. Okay, now this is another circuit. If you see here, here two resistors are always connected here. So, whenever this input signal, suppose I assume that input signal is 0 out here, right? So, I will have 0 out here. So, this will be 1 here. So, this is switched off, initial condition. Okay, this will be switched on. I have a 0 out here. So, I have 3 inverters. I have a 1 out here. So, because of that one, this will also be 0 out here, right? So, this will be switched off. So, when I have a constant 0 out here, there will be 1 here, there will be 0 here. So, this transistor will be switched off, this also will be switched off, and the output will be at VDD by 2. Okay, so this output is at VDD by 2. Okay, now suppose this input is making a transition from 0 to 1 out here, right? So, whenever this input transition is making from 0 to input is making a transition from 0 to 1 out here, right? So, now it was 0 here, so this is 1 is available here. So, 1 is also available here. So, you will have a 1 here. So, this gets turned on. So, if it gets turned on, you will find that this output will rise high. But by the time, okay, after 3 inverter delay, since it is 1 here, it will become 0 here. Okay, that 0 once it reaches here, this will again turn off. So, now this voltage will this will get turned off, and because you have connected two resistance here, it will come back to VDD here. Okay, is this much aspect clear to all of you? Let me explain you once again out here. You have two resistances here. So, when input is 0 here, right, this will be 1 here, this will be 0 here. So, both these transistors will be switched off in this case. So, the output will be VDD by 2. Whenever this input is making a transition from 0 to 1 here, so there is a delay element out here. So, the moment 1 comes here, this will get switched on and the output will go to VDD. And then subsequently that 1 gets comes from 1 inverter, 2 inverter, 3 inverter, it comes as a 0 here, and then this will go back to 1 and this PMOS will be switched off. And once it is switched off, because of these two balancing resistors, the voltage will come back to 0. So, whenever the input is switching from 0 to 1, you will have a small the output being raised to VDD, and then it will come back to VDD. Similarly, if the input is going from high to low, right, the moment it goes into a low here, so there is an 0 here, so this will get an switched on out here, right. So, if it is high here, there is a 0 here, right. Initially 1 will be available out here, right, and then 1 is available here, right. So, the moment it goes to 0 here, so that 0 which is coming here, okay, will switch on this transistor. So, you will find the output getting grounded, but subsequently that 0 will come here as 1, again you will have one more 0 here. So, both will become 0, then this will get again switched off. So, for a short duration, this will be pulled towards to the ground, and then once that gets switched off, because of these two resistance, it will come back to half VDD. So, what this circuit does is, okay, normally if the data is stable, the output will be VDD by 2. Whenever the data is going from low to high, it will give a spike like this, it will go to VDD and come back. And whenever there is an data which is going from high to, when the data input data out here is going from high to low, it will go to ground and then again come back to VDD by 2. Okay, so you are only sending the differential signals out here. Okay, so the receiving signal part has to just check for these spikes and accordingly decide whether the output is high or low. Is this understood by all of you? Okay, how this circuit works. Okay. So, now if you see here, why do we call enable as a clock signal? Yeah, this is an enable signal. Yeah, you can call it. It is just we are calling this is an enable signal only. So you can call it as enable whenever we want this data to be transmitted. So it is just the nomenclature what we use. Okay. Now this is the kind of signals which is received here. Now if you see here, this is a particular circuit which on the receiving side. So you have these in and in bar. If the in signal is going high, okay, if you will find that it is again a cross coupled latch. So an increase in this signal, okay, here this will switch on this NMOS, and this voltage will drop, and that voltage drop will switch off on will switch on this PMOS. So this will go high, and this feedback is given here. So this will be switched off. So that will enable further. So it is a positive feedback circuit. So this kind of circuits can be used when the output signal is like this. Okay, this is the, we said in the previous signal, this is going to be the on chip final IO pad. Okay, so we are going to send, instead of 1 0, we are going to send these kind of signals. Okay, it will be VDD by 2 generally, and whenever the signal is going from 0 to 1, it will make a spike out here, and similarly when this input is going from 1 to 0, it will make a spike from VDD to 0. And these kind of particular circuits will be used in the receiving side to generate back the proper digital output. Okay, so by using this circuit, the advantage is that there is no large power which is consumed here, and there is no drop in voltage in the bonding wires and all, because there will be lot of parasitics in the chip bonding and things. So and in the bus lines which are there from connecting one chip to other. So to prevent that, this is the kind of signal which we use. Okay, instead of using a proper 1 and 0, we can use these kind of signals also. Okay, so that is, and then coming to the last part of this is packages. Okay, so now what is the function of packages is electrical connection of signals and power from the chip to the PCB board. There should be little delay or distortion. A mechanical connection of the chip to the board removes heat. Okay, so whatever heat is generated in your circuits, that needs to be dissipated, and mechanical damage to the actual silicon chip compatible with, because of heat, it will these chips will expand a little bit, so that needs to be taken care of, and it should be it should not be very costly. So these are some of the functions of package. So the several kinds of packages are available. Now once you make a chip, so finally when you give it to the fab lab, so depending on the number of pins which you have, and the amount of currents which are required, so you will select the package. So there are several kinds of packages which are available. These are given by the fab lab. So you have to select, once you design a circuit, before sending it for the fabrication, you will have to tell the fab lab you finally want your circuit in this particular package. Okay, so dual line package, this is what it looks like, right? These are the dual line packages. Okay, normals where both lines you have the pins coming out here, and then you have a pin grid array. Okay, pin grid arrays like this, right? You have all the pins being projected out here, and then you should have a corresponding right, and a socket. So you plug this into that particular socket. So the socket will be soldered onto the PCB. So this chip, you just push it into the socket out here, right? This also there will be a corresponding socket. So here also you plug in this socket. Okay, so that this is known as a pin grid array. Then you have a plastic leadless chip carrier. So if you see here, this is a PLCC. In which there are no pins which are on the surface itself, here itself. Okay, there will be some metal pins available here. They are not pins which are protruding out. It is so you will have to use the SMD technique to solder this onto your PCBs. Okay, so here you can this is generally without SMD you can't do these kind of chips. You can't mount these onto PCB. So these are known as the PLCC. Then you have a ball grid array also. So if you see here, this is an on a ball grid array. So this Xilinx processor is an 560 pin. So you have a small ball, semicircular balls which are there on the surface of the chip. So each one acts like a pin. So you have a corresponding socket also which will be there on the PCB. So you have to put that onto that socket. Then it makes a connection. You could have an quad flat pack also, like there is an example figure given here. Where is the here? Like there are pins all around, all the four sides. Here this only 12. This is a dual. This is a quad. All the four sides, you could have pins, and a thin small outline package. Okay, this is. So these are the various kinds of packages which are available. Now this is again Pentium Pro MCM processor. This chip, if you see, this is the microprocessor, and these are all the pins available here. You could have a cache also, an external cache memory also, which is placed close to the chip here, right? We know why a cache memory is used, right? Because some portion of the from the RAM is brought into the cache memory, which is very oftenly used by the program, so that it can. These are generally SRAMs; they are not dynamic RAMs. They are SRAM chips. So some portion of the program which is constantly being referred to, that will be brought into the cache memory, so that it speeds up the overall speed of the operation, right? So you can have. See, each depend, like all these packages, they come for different current ratings and all, right? So you generally you have these pins and all for high current ratings, where it makes an large area contact, right? Whereas these things, they make very the area of contact, if you see, they are very minimal. So depending on power and application, so that you have to choose. So when you see the package specifications, each one will be different. Okay, even the size of these things also will be different, and accordingly depending on the circuit and technology node as well. Yeah, so you will have to select what is the package which is available to you, right? So that is what, right? These kind of packages are also used. And this is how a traditional things looks like. The chip will be only this much, okay, and you have a huge area, and these pins will be brought out, so that the heat is spread evenly. This entire thing will collect the heat from here, and it will get dissipated. So you will have a heat spreader, and this is the bonding wires from this chip to these pins. So they act like an inductor, and that is what we studied earlier. Okay. So these are some of the chip to package bondings. Okay, and now the heat dissipation is a very important factor. So although we might think this small ICs, and why should we so much be bothered about heat, but that's not the case. If you see a 60 watt bulb, earlier days what we have, not the LED one, it had a surface area of 120, and those bulbs you couldn't touch with your hand, right? It used to get so heated up. Now if you see these are Itanium, which is an old processor. It used to, these days though, they generate much more higher power. So 130 watt over 4 centimeter square. So you will find that per unit area, the amount of heat which is generated is much higher. Okay. Because so you will find these chips can get much hotter than your incandescent bulbs, right? So you will find that and hence you will find most of the modern day processors you require a fan, and you also employ liquid cooling these days. So many high end processors they use a water cooler itself. You have a lot of master coolers which are there, which run water in small through small orifices, and that cools the IC. On top of that IC, you place a cooling system. So that is the heat dissipation is a major issue these days. So you will have to take care of these. Okay. So with that, we will stop it for today. In the next class, probably we will see a modeling of wires. Okay. Thanks a lot.